We'll start up in a minute or two here. Assume Chris is back with us.
Yeah.
Okay, good. Excellent. Just see, there's 20. Why don't we just wait one more minute, Chris, then you can start. Okay, why don't you take it away, Chris? I think you've got it.
All right. Great. All right. Let me share the screen. All right. So hold on. Once again, this is going to sort of be a kind of a recap of everything we've talked about in the last 2 days. Just going through an example run deck that actually came out of one of Mike's publications on Proxima B. And once again, I had talked about this before the break, but if you do want to follow along, you still have time to just download the files in the second link here, and then put the run deck in the decks directory, put all the other files in your input files directory. And there's a slight modification to make to the run deck to find the Socrates files. So that's on slide 79, I think, of the tutorial. All right. So this is kind of just cover everything we've talked about and just have it sort of condensed into one little talk. Repetition is quite nice for something like this. I'm assuming everyone can see my screen. So the run deck is this ProxB tutorial. And so when you're starting to make a planet, you will need to generate a run deck. So this is based on the P1. It's basically, you know, a modified form of the P1 SO M40 run deck, which is your Socrates radiation 40 layer dynamic ocean run deck. And then you'll just need to go to this model E/model/shared directory, and then you'll have to modify this planet params mod F90 as we've talked about. And I think you should already have ProxB in there. I checked that last night, that the version you've downloaded is already in there. I have a lot more planets, but let's see, where's ProxB? Let's see if I can actually find it in here. I have a lot more things than you will. And whatever, it's somewhere in here. But whatever, it's not, all right, I can't find it, but whatever. But it should be in there. You'll have, so the name will be ProxB. And that is, if you go back to the run deck, that is going to be, you're going to see that in a couple places. ProxNB here at the top, and then kind of in the middle of the run deck is going to be, it's going to be somewhere else as well, down in planet
Chris, did you
name.
put the planet params entry for ProxNB on in your source file directories for this example?
Yeah, it's actually already there for the participants of this. I mean, I have it, but yeah, here it is.
Yeah, there it is.
Yeah,
you have to have this in before you can do anything, of course. So just pointing it out.
But I do think everybody has it in theirs. You might have only a couple examples. Okay. So there is I will share this document as well, but this is going to be helpful as well, since this is a written document of everything I'll be going through. And I'll share that in the window briefly, but now I can't even open the window. All right. So yeah. So a lot of the units are obvious. You have to declare your gravity. So the radius in meters, the molecular weight of the air. You do have to put that, which is just I think Igor mentioned maybe yesterday that this is just a sort of fractional weighted sum of the molecular weights of everything you have in your atmosphere. The surface pressure in millibars. The ratio of Cp to Cv is this SRAT number. These are a few thermodynamic things that, you know, if you have these wrong, the model will still run. So you want to make sure they're right. And then your fraction of your major constituents. So this is basically a pure N2 atmosphere. You might see some small deviations if you expect to have some greenhouse gases in your atmosphere. The greenhouse gases will not be set in this file. They'll be set elsewhere. You can also have pH2 if you have hydrogen in your atmosphere. All right, so this is all set up. You can use these as examples for any, if you want to create a new planet, whatever it happens to be called, just copy and paste this segment and then change the values accordingly. And that's all I'll say about that because we've covered that a little bit. All right. All right, so now we're gonna go back to the run deck. At the top, you can, it's good to write some comments about this. This section up here doesn't require comments, but comment like explanation points. But you can you just write some notes about your run, just so you know for sharing purposes, and so you know what you did. So this ProxB run is an 11.2 day Earth day orbital period and rotation period, so it's a synchronous rotator. The solar constant is about 881 watts per square meter. And that's just a few notes about the model. But all right, so just going down this list here, a lot of these things are not going to be changed in general. They may vary by run deck, depending on your ocean configuration and such. Do change the planet name to ProxNB, which is what you declared in that last Fortran file we looked at. And then most of the stuff up in through here, you won't be changing. This just kind of calls on your model files and the radiation files. Okay, usually the first thing you're gonna start to be changing for your particular planet and is your input files. Now I have two sets of possible input files, kind of a choose your own adventure if you are following along. I have a, and these should all be in the input files that I provided. So this one's for an aquaplanet. You just uncomment these lines if you want to do an aquaplanet, and then comment these lines out. What I'm going to be doing is, this is with Earth continents, so they're going to have, these actually have the same atmospheric initial conditions. You'll find the AIC file, you want to be a little strategic in that it's nice to have a something that isn't going to be a huge shock to the system when you start the run. So if you start with you know, -200 temperatures or something like that, then you know it might be a big shock at the first time step. But usually a lot of these AIC files are just I think this one in particular is just a uniform temperature at 285 Kelvin. Actually, I have this in Panoply, so you can just see the structure of these. The input files are, you know, so you would just put sea level pressure, and this is just the same pressure that we saw in the Fortran file. This one is a 984 millibar pressure, so we're starting the input file at that pressure. It can actually be different, but there's no reason. It will end up being a 984 millibar pressure, and kind of keep those numbers the same. And then if you do the column T, so this is a 3-dimensional thing, and then T serves 2-dimensional, but it's starting at a uniform 285 Kelvin temperature, and there's no winds. So if you do UV, it'll be 0. That's this particular input file, but and you'll find the OIC file is maybe slightly more complex. It involves some weird variables like specific enthalpy and such, but we do have OIC files available for almost any run you need, or you can at least follow the logic of the OIC files we have and then just do a different land C mask, for example. But you can contact us if you need help with that. You do need unique OIC files for a given mask, however, for if you're doing a new topography. So topo here is, I'll just show you the example of what that looks like. And again, this is going to be Earth continents. So you're going to see the fraction of ocean. So I'll just click on that. It's going to be ones and zeros, as I think Igor mentioned yesterday. It's a grid box is either land or ocean. So these are ones over the ocean, and now for land, it can also be so it's ones for land, but it can also be ice. For example, if you have an ice sheet, this particular one doesn't have an ice sheet, but if you want Antarctica, for example, as an ice sheet, remember there's no dynamic ice sheet in this model, so you would just kind of prescribe an ice sheet. Now, just be careful if you're doing a, like a high obliquity planet, right, where you expect the poles to get really hot, and you have the Antarctic ice sheet where Antarctica is, then it might not be a particularly realistic simulation. Now, the model will allow snow to accumulate or melt where it wants to, but the ice sheet itself is not a dynamic entity, so it will just sort of remain there throughout the duration of your run, even if the temperature is really hot. So for this particular example, there is no ice sheets. And then topo OC is your ocean, your ocean sort of topography, or if you will. These F oceans and should also be consistent among topo OC and topo. And then Z ocean is your ocean depth. So that's where you're going to set that. This particular example is I guess a 13, it's basically 1360 meters steep everywhere, except there's a couple right along the coast. There's a little bit of a gradient to the land. But that's where you would set your ocean depth to somewhere. And again, it's nice to consult the ORES file to see how deep each level goes. I think traditional, I don't know if this is required. Traditionally, we've done things at the endpoints of different ocean levels, and then we go down to almost 5 kilometers in the 13 layer version. But you can go to the bottom of the 5th layer, for example, which is a few hundred meters at the bottom of the 7th layer if you want a shallower ocean. And you do that especially if you expect that you want to reduce your equilibration time, because most of what takes these runs a long time to come to equilibrium is the ocean heat capacity, right? So if you have a shallower ocean and that doesn't really matter much for your particular run, then you might want to do that. I won't go through a couple of these input files like ground. They're a little esoteric, I think, for this purpose. Now, we have talked about the river directions as well. The model will run without rivers, but again, we talked about this issue of potentially accumulating kilometer-high columns of lakes if that water has nowhere to go. And so we do have river input files. You can potentially use the ones that we've provided, or if you need to make your own, you probably want to contact Mike. He probably is the best person right now for creating a custom river direction file. and also ocean straits that Costas was mentioning yesterday as sort of a parameterized way of representing water flow through areas with this topography, but it's too narrow to be resolved by the model. Okay. So again, you can, if you want to do this in aquaplanet or Earth continent mode, just comment the appropriate lines. It won't matter. If you have an aquaplanet, some of these things like river flows, you can use either file. It won't matter too much because you don't have rivers on an aquaplanet, except at the one South Pole point potentially. Okay, and just a few other input files we want to be thinking about are the soil textures. Again, this is just I guess this is a clay sand mixture that we have a lot of these input files available. If you look at the netcdf file, I think Igor was showing earlier that the variables like Q and QK, they might be a little strange to look at, but we do have a lot of these available. And then the vegetation is where, so you can set this on an aquaplanet as well. It won't matter if there's ocean. This is just not relevant over ocean, even if the netcdf file has values over the ocean. But so you can set your surface albedos, and I guess we'd have to, somewhere we'd have to look up what the albedos of these surfaces are. I don't exactly know where that information is located offhand. But all of these types have a certain albedo associated with it. And so if you wanted to sort of know what your surface albedo was, then it would just be a fractional weighted sum of bright soil and dark soil and all these things. You could see this thing is has 0.5 or whatever, or 0.4 of bright soil, and it has 0.6 of dark soil as well. So if wherever you do have land, that would be the surface type. Now, of course, you can also accumulate snow or lakes on parts of your land surface that will modify the surface albedo, but this is sort of your, bare ground state. And then the GLMount file was briefly mentioned yesterday as well. That is where you will have icebergs kind of being dumped into an ocean, if you do have ocean, and be careful if you're on a land planet, and because you don't have ocean, but I'll mention this briefly momentarily, because we do have that WSN max parameter that prevents snow from accumulating indefinitely. And then so anything above that WSN max value is dumped into the ocean, and you could set sort of where it's dumped into the ocean through this netcdf file. I don't have this open right now, but if it's just a mask of like ones and zeros where you want that to go. Okay. Some of these are not necessary. K-Basin, for example, just gives you diagnostics for certain ocean basins like the Atlantic or the Pacific, but for exoplanets, that usually doesn't have a lot of meaning. So I think you can even comment these out. But all right. The GHG file is just a text file. It's very, very basic. And let me see if I have, let's show you the format of these. Here it is. So I catted the GHG proxb file. So this is a 376 ppm file here. It's just a text file, and just modify that. The year I don't think will matter. So yeah, that's the only place where you need to set your greenhouse gases. And for that particular run, it's just CO2 in the atmosphere. I'm getting my windows mixed up. So there's no N2O, there's no methane, there's no CFCs. So this is just an N2 CO2 atmosphere. O3, so there's no ozone is turned off by default in the rundex. But if you do need ozone for whatever reason, you can do it as an input file. This is assuming you're not doing things with interactive chemistry and such, which I'm not talking about in this tutorial. But if you do need to do some of that stuff, you can talk to Costas probably, or Sunny as well. But otherwise, you could just, if you do need ozone for whatever reason, you could do an input file that is, so it's just a prescribed ozone distribution. Okay, now we're going to get to some of these things might be redundant, but it's good as just a safety check. So again, this is a pure N2 atmosphere, so we're zeroing out basically everything. And CO2x equals 1. So if you know, in that text file, it was 376 ppm. If you change this to 2, it will double that. So just be careful. We typically recommend you keep this at 1 and just, you know, people have mixed opinions about the best way to do this, but just be careful if you change the text file and this is a number other than 1, you know, it will multiply that number. So just make sure you don't do any double counting or anything. Okay. And then we have to figure out what type of star or planet is orbiting. In this case, it's Proxima b. This information is found in the stellar spectra folder. Too many windows going on. All right, here it is. So these are some current, some of these you might not have, but these are some current options. There's the sun, of course, and PC is here. You can actually, you know, open these files and plot the spectrum just to see what the wavelength distribution is. But so that is where your star is. And then your spectral files, as Eric talked about today, have to be chosen somewhat strategically based on the star atmosphere combination, right? So it's not just the star, it's not just the atmosphere, it's sort of how those two work together. And these are some options in your spectral files directory. You're going to see all these kind of different options, and we do have a document which I think was given at some point to everyone. If not, we do have a document that goes in detail about which spectral file you will choose for a given star atmosphere combination. And so for like a 10-bar hydrogen atmosphere, for example, you would choose very different spectral files. These ones are, actually, I don't even know if these are the best options for this particular run, but these are pretty fast default Earth spectral files, which you can just look at and just kind of see what's going on here. Okay. All right, so now we've set up our topography, we've set up our the star, the spectral files, the input files, and so now the solar constant is this planet S0 parameter. So this is your 81.7 watts per square meter. The Earth value is about 1360. So if you don't have this in there, it'll default to that. And this is the only place that this needs to be put in. There was that mean distance parameter that was mentioned before. I wouldn't recommend introducing that into the run deck. It's not there, and it doesn't need to be there. You will need to, let me skip this real quick and jump to here for your orbital parameters. Okay, so this is the other place, planet name, where you're gonna write proxnb. And again, if you don't have this line, everything's gonna default to Earth. And you also need to explicitly write the eccentricity, the obliquity. Again, if you don't have these, it won't default to 0, it'll default to Earth. sidereal orbital period and rotation period. So for a synchronous planet, they're the same. So that's shown here. You actually can do a negative rotation period for retrograde rotation, if that's what you're doing. But the calculation is very simple. So it's an 11-day or 11 Earth day orbital period, and just do the calculation, convert to seconds, and put that in there. And Tom talked about the quantized year length parameter, which is usually going to be true. Back up to here, just based on our experience running these simulations, there's going to be some sort of things that you might want to introduce into the run deck that aren't there by default, that sort of helps you avoid some error messages that are routinely encountered. This RTAL parameter has to do with kind of controlling the drag up at the top of the atmosphere so the winds don't go crazy. And there's some temperature bounds that you might need to change if you get outside sort of the Earth temperature regime. The model might think you're doing something weird, but just tell it you're not. So there's a few of these things which you can just sort of copy and paste, and you should avoid a lot of crashes that are routinely encountered. All right, so that is most of our planet. Now, a lot of these things probably don't need to be changed. We have talked about whether your lakes are dynamic or not. So that's this parameter, which could be set to 1. In this run deck, K ocean is 1 by default. That's the dynamic ocean, so you shouldn't need to change that. This was our snow depth restriction parameter, which is it's 2 meters by default, and if it's 0, then there's no restriction on the snow buildup over land. So a lot of this stuff is just it takes a few hours to set up a planet and just kind of make sure everything is kind of what you want it to be. And most of these things down here you won't be changing. These are various tuning parameters that are fixed for a given run deck for the most part, and so you probably should not, once you find a run deck that template that you want to use, you probably don't need to mess with most of these things. Costas did talk about this master year if you're doing a transient run with real years, but for exoplanets, we're not usually doing that, so you won't have to change these things. There is some time step things that you might actually need to change periodically, either in the event of model crashes or if you just anticipate that your planet is going to be pretty hot or pretty cold or pretty different from, you're gonna invoke a pretty large shock to the system relative to the initial conditions. It might be safe to reduce these time steps from the default values. And there was this crash solution document that was passed around that provides some guidance on how to do that appropriately. So could consult that document. These are a few other things you might want to check. So cloud radiative forcing controls some output. Basically, a cloud radiative forcing is the radiation calculation is called twice with and without. One calculation assumes the clouds are transparent to radiation, so that kind of helps with some, if you're going to investigate the radiative impact of clouds, you could set that to 1. It seems we've had some discussion about whether this actually slows down runs, and it should, but in Socrates, it doesn't seem to have a big impact for whatever reason. But I don't know. All right. This KRSF file is going to generate, this is going to set the frequency of your restart files, RSF files, and this is going to be in months, so you'll get an RSF restart file every 10 years if it's 120. And this it's good to have some restart files being generated, because if your model crashes, then you can always go back to a restart file without just rerunning the whole simulation. On the other hand, restart files take up a lot of disk space. They're quite big, so you probably don't want a restart file for every month. So some, find an acceptable value. If I lose 10 years of a simulation, it's not going to be the end of the world. So find an acceptable trade-off value. There is this parameter MANAV, which we haven't talked about, but this actually is useful for the accumulation period of your output. So if you have, we've mentioned that the default file output for the ACC files is monthly, but say you don't want monthly, you want annual, you would set this to 12. If you want every 10 years, it would be 120, right? And this is good, especially for a planet like this, when you have an 11-day orbital period. What's going to happen, you'll find, is that one orbit is very, very fast, and 1 month is 1/12 of that, right? And so you're going to start up your run, you're going to go get lunch, and you're going to come back, and you're already going to have 100 orbits or 100 years, because they're 11 days long, right? And so that's going to eat up a lot of disk space. So rather than having monthly output, you might want yearly or decadal output being automatically generated. And for most cases, monthly output doesn't actually mean anything useful for a very short period planet, right? Like January of a 11-day orbital period planet. It doesn't really mean much. It might be 6 hours long, right? So you might not lose much by just averaging over some of that by default. You just can't go back and retrieve those files. So, and then year I, year E, we've talked a little bit about this. Is just going to be the start date of your run, which for exoplanets, the actual value doesn't really matter much. It's, I find it intuitive to start at 1. And Mike mentioned also you can have this as a 5 and maybe even a 6-digit value. So you would do that, and then something like that. If you expect this to go very long, again, if you're doing a very short period planet, like a 10-day orbital period planet, a year means an orbit. So you might actually get into 5-digit years before you get to equilibrium. Otherwise, you could just sort of use these numbers for most purposes. These things don't usually require much changing. The iStart value should be 2 by default. The only exceptions, which I have written both in the document and also up here. If you are starting from a restart file, you could set it to 8 or actually 9 if you're doing a different. If you're doing the same run, a restart file from a different run would be iStart 8. So I should fix that, but I think it's written correctly in the document I provide that I have creating a new planet, which is also in the PowerPoint. You would do this also, for example, if you're doing a snowball, like people are interested in hysteresis and whether snowball states are reversible or not. So, one thing you could do is run a very cold experiment that will freeze over, let it freeze over, and then take a restart file from that run and put it into a new run deck as your AIC file. You would just set this to the RSF file, and then iStart equals 8, and then you're going to start in a snowball condition, and then you could run your simulation. Okay. All right, so that's the run deck. And are there any questions at this point? Before I jump. Okay. Have there been questions on the chat window? I can't look right now.
No questions, no. Nothing to worry about.
We've been taking care of them.
Okay, great. All right, so hopefully that all makes sense. Now we're going to run the model, and if you do if you did want to follow along, I would just follow the few commands that were provided in the ROCKE-3D install computer. So the proxb run deck should be in your decks directory. You're just going to change, obviously, instead of P1 SOM4 test, you're going to do the proxb tutorial. I just changed the run name. Make sure your input files, so there's this line up here, which makes sure your input files are there. And so you can run the simulation, and yeah, so if you do this command, this will give you a probably not even a month of output. You're just going to have a partial ACC file, I think, but you can do all the commands with that as well. One thing I'll mention first too is we can look at in the Dex directory. I already have a few years accumulated here, but you might just have a partial ACC file. I think Igor mentioned you can look at the PRT file. If you do the first 100 lines or something, this tells you this gives you some sanity checks about your orbital parameters. So this is the rotation period, the solar day, and some of this is just sort of spitting back information you provided. This is the sort of to gain an intuition for how the calendaring system is working. You can look at the sort of number of pseudo days in each month. So an annual average, by the way, this is automatically done in this when you do some files, and but it's just going to be a weighted average of the number of days in each month. So just kind of being aware of what those things mean is useful. All right. So now I have some output. Now, this is, I think, also in your huge space directory for everyone. I think that's how the setup was done for people who don't, for people who just installed this. I think that was the name of the directory that your output
that's right.
will be.
That's right, Chris.
Okay. So in your huge space directory, you're going to start, you might see just one partial ACC file. If you run the model a little bit longer, this will start populating with more ACC files for every orbit or for every month, depending on how you set up your NMANAV parameter. I had NMANAV to 12, so I skip the monthly output and I just get annual output. And so we can scale ACC any of these. So scale ACC, say the 8th orbit it could be AIJL or OIJ for the different output diagnostics. And I think you could write all to get all of the available things. And so what I'm going to show here again is just, so at this point if you have an AIJ file or an OIJ file or whatever, you now have everything you need to start looking at what the climate is doing. And again, you want to run the model in practice. You want to run it long enough to reach equilibrium, which you can check by, and typically you want to do an average over 10 or 20 years, not just 1 year, but for right now, I'll just show the value for one orbit, and this is going to be NetRad planet. HEMIS actually gives just the global average value, and it's this number. This is in 8 orbits. It's currently 105 watts per square meter out of equilibrium. Okay, so this is not this is not in equilibrium. All right. We've only run 8 orbits of an 11-day orbital period planet, so it should not be in equilibrium. have to run it much longer. But we will look at that AIJ file here. I brought it over here. A few things I always recommend looking at before doing any analysis is, first of all, we're going to look at INCSW_TOA. That is your incident solar radiation. Always double check to make sure this looks like what you think it should look like. And you might actually have to do it over many orbits to make sure it's not moving in any weird way. But since we're doing a synchronous rotator, this is kind of the pattern that you expect. And if it looks very different, right, if it's like a longitudinally uniform insolation pattern, then you know you did it wrong. So this is always good to check what the installation pattern is. And net rad planet is in here as well, but we just looked at that value. Of course, T-surf is surface air temperature, which and they have continental outlines. I think in Panoply, I think the actual topography we used is not provided by default in Panoply, so you'll have to maybe change the mask to something else that you could probably get a relevant file from one of us. Notice that the temperatures this is a bad color bar for temperature, so you could change your color bars here. Notice that in this run, so what's happening here, the land got very cold real quick because this is going to end up being a colder planet than Earth. And remember, we just started this from Earth-like initial conditions, and this planet is 100 watts per square meter out of equilibrium. So the land is cooling very rapidly first, and the ocean hasn't really done anything yet because there's a lot of heat capacity in the ocean. So when you run this to equilibrium, it's going to look very different. And all you're seeing in this file in the 8th orbit is that the land has gotten really cold really quickly. But by the time you get this to equilibrium, you're going to have a very different temperature structure. Particularly, you're going to have a substellar, kind of, representation of the climate. Okay. Yeah, and I think at this point, that was a very quick introduction, but I think at this point, I will just take questions.
Okay, great. Thanks, Chris. Do we have any more questions for Chris before we go for a break? Otherwise, you can ask them after the break, when it's going to be all up to you all to decide what questions you have. And if you don't have any questions, we get to go home early today. So
Igor asked if you increase the eccentricity. So this is a good question. So the planet S0 is it's the solar flux at the semi-major axis, right? So if you increase the eccentricity, what you'll find is that okay, so let's look at this INCSWTOA. You can actually get the mean value from also that. Actually, I should just do the hemisphere values. So this is so 220.5. That's the global average solar radiation. And you could do a sanity check by multiplying that value by 4. That gives you the 880 whatever solar constant. The reason you multiply by 4 is because the Earth's a sphere, and the solar constant's defined as sort of what's hitting a kind of a perpendicular wall at the Earth, at the planet star distance, and it's the cross section, right? So it's the ratio of 4 pi r squared to pi r squared. So anyway, but the long story is you multiply this by 4, and that should be your planet S0. For an eccentric orbit, however, this number will be different. It will be a little bit higher. because eccentricity does increase the total annual mean stellar flux on a planet. So it will be slightly higher if you do an eccentric orbit. But the planet S0 is it's just the value at the semi-major axis.
Yep.
Stephen, I don't think you need to change an AIC file for retrograde rotation. Actually, in these AIC files, the winds start off at 0, so there is no motion initially, and as the model starts iterating forward, the winds will start to pick up.
Yeah, you can imagine there's a reason for that, because probably when we first ran these simulations, we used earth wind fields. And when the model started up, it became extremely unhappy and unstable. So we went with 0 wind speeds. You can start up almost any model with that. It's a bit safer. Okay, shall we take a 15-minute break? And then again, as I said, whatever questions you all have, that'll be your chance to ask them. So it'll be another 45 minutes worth of question and answer. That's all it is. So anything you have a question about, no matter how silly you think it is or how uncomfortable you are asking it, now is the time. We're all here. There's no silly questions because this is new to every one of you. So so we'll meet up again at around quarter after, I guess. I guess that's quarter after 2, and we'll go till 3, or we'll go shorter if you don't have more questions. So think about questions you might have. Okay, we'll take a quick break then. See you in about 15 minutes. Thanks again, Chris.